The next method of preparation of alkenes is the dehalogenation of vicinal dihalides. It means we have to remove halogen atom from vicinal dihalides. Vicinal dihalides are those halides in which halogen atoms are attached to adjacent carbon. For example, here we have, let us suppose, 4 carbon compound and the halogen atoms are attached on 2 adjacent carbon atom. Then these is known as vicinal dihalide because of 2 halogen atom, and vicinal because of adjacent. So vicinal dihalides, they have 2 halogens on adjacent carbon atoms. Dehalogenation will occur when a dihalide will be treated with zinc dust in anhydrous solvent like methane or acetic acid, which means that vicinal dihalide will be treated with zinc in the presence of any anhydrous solvent such as methanol or acetic acid, and it will result in the formation of alkene plus zinc halide. Now let us see this with the help of an example. Now this is a vicinal dibromide. We will react it with zinc in the presence of methyl alcohol. Both the bromine atoms will join zinc and the rest will be, the bond will become free, plus this zinc bromide. This is the product. So we will get 2-butene as well as zinc bromide. So this is the preparation of alkenes with the help of vicinal dihalides. Now let us see the preparation of alkenes with the help of Kolb's electrolysis. This is basically the electrolysis of salts of dicarboxylic acid. When sodium or potassium salts of dicarboxylic acids like succinic acid, etc., they are subjected to electrolysis and the medium is aqueous medium, the alkenes are formed. For example, here we will take disodium succinate. It will ionize in aqueous medium. To give anions and cations. 2 sodium ions will be the cations. This is disodium succinate. Now first of all, reactions at anode. Anode is basically positively charged because negative ion or anions will move towards it. So at anode the reaction will be like this. Now I have opened this structure. This structure is opened here, just so that understanding is easy. This will give its 2 electrons, mean 2 electrons will be removed and it will become the radical. Oxygen has an additional negative charge. When we will remove 2 electrons, the electron will be unpaired. Now this will further give two molecules of carbon dioxide when this is carbon dioxide, CO2 and CO2. When this will be removed, this bond will become free, and ultimately they will be attached by a double bond with two carbon dioxide molecules. Now at cathode, the cations or the sodium ions, first of all, water will gain these two electrons that are removed from here, and it will be ionized to hydroxyl ions and hydrogen gas. The hydrogen gas will be removed from the system. Now these two sodium ions and two OH ions or hydroxyl ion will combine to form sodium hydroxide. So this is basically the called electrolysis, in which we use the dicarboxylic. Dicarboxylic means two carboxyl groups are present, so we will use a dicarboxylic salt of either sodium or potassium. So here we are using disodium succinate. Initially it will be ionized in the presence of aqueous medium into anions and cations. The anions will move towards the anode, which is positively charged, and anions will lose the two electrons. Ultimately they will be the radicals, and after losing two molecules of carbon dioxide, they will give required alkene. And at the same time, the sodium will move towards the cathode. At cathode, water will take the two electrons given by succinate ion, and it will be ionized to give two hydroxyl ions with liberation of hydrogen gas. The hydroxyl group will join with sodium, and it will give ultimately sodium hydroxide. Now the last method of production of alkenes is partial hydrogenation of alkynes. Partial means alkynes have triple bond, and if we do hydrogenation at first step, the triple bond will be converted to double bond, and we will stop the reaction right there. If we go on further and will add further hydrogen, it will be converted to alkane. So we will carry on the controlled hydrogenation of alkynes with hydrogen gas in equimolar ratio, and we will use a heated catalyst, so it will give us alkenes. The catalyst will be finely divided palladium, which is supported on barium sulfate. This is going to be the catalyst, and it is also poisoned by treating with quinoline. So this will become a catalyst which is known as Lindlar's catalyst. So basically we are using Lindlar's catalyst in order to carry on the reaction. So here we can also observe cis trans alkenes. Let us take an example. First of all, addition of hydrogen, partial addition, the catalyst, Lindlar's catalyst, and we will get alkene. Hydrogen is added here. This is the cis alkene. Now if you want to obtain the trans alkene, you will treat this alkyne with sodium in liquid ammonia at minus 33 degrees centigrade. You will lower the temperature of the system. For example, let's see. We will use atomic hydrogen or nascent hydrogen. The catalyst now will be sodium in liquid ammonia, and the temperature is going to be minus 33 degrees centigrade, and this will give you, this was cis alkene, and now we will obtain the trans alkene. So the question may be asked that what is the role of Linder's catalyst in the production of alkenes, or how can we obtain cis and trans alkenes, give the method of production. So you should be very clear about the concept. That is all about today. I hope the lecture is very much clear to all of you. If you have any questions, you can ask in the comment section. In the next video, we will talk about the properties, both physical and chemical, of alkenes, and we will discuss the reactivity and different reactions of alkenes. Till then, take care of yourself, keep studying. Allah Hafiz.